Today we're going to be covering section 9, which is on understanding independence. We're continuing to build on that idea. And so you can see here at the top, understanding independence, it says, we have spoken before about the idea of independence, and we have given a definition, but chances are that you still don't fully understand what it means for events to be independent. Based on your life experiences, you probably would not be surprised to learn that whether the temperature is above 70 degrees and whether a person is wearing shorts are not independent, right? The hotter the temperature, the more likely a person will be wearing shorts, right? Obviously, it's dependent on the type of person, but anyways. Likewise, it probably doesn't surprise you that rolling a 6 on a die and flipping a head on a coin are independent, meaning one doesn't affect the other. But what about when it's less obvious? Are gender and incarceration rate independent? Are race and incarceration rate independent? If so, what does it mean? If not, what does that tell us? We're going to use the tools we have developed thus far to explore this a bit further. So 1, are the events participates in extracurricular activities and know what I want to do after high school, independent or dependent? So what do you guys think? Do you think that your friends, right, that their participation in extracurricular activities is dependent or independent of whether or not they know what they want to do after high school? Dependent, okay. And how would you justify that? Okay, so someone that knows what they want to do after high school would be exploring that, right? Doing things to help advance that, right? Okay, I get it. Would anyone say anything different? I might argue, oh, they're independent. I mean, some people play sports. What does that have to do with what they want to do after, right? And they just need that workout, that brain break, that physical activity, right? So, um, right? And then someone might say, but Mr. Labus, right? Um, People that are in sports are more likely to um, have a good, work school life balance because they have to balance having less time to get stuff done, and so they're more responsible and things like that. So, anyways, lots of discussion could come out of that, right? All right, so let's look at some data here that they give in this table. It says fill in the table below. Now, it looks like we definitely have some empty spaces here. So let's look at this column here because there's only one empty cell. And we know that the 800 plus whatever is in the cell has to be 1,000. So it's a 1,000 two-way table. What's going to go in this cell? 200. So, and then we can do the same thing for this row, right? There's only one empty cell. We know that 600 plus something has to equal 1,000. So what is this cell going to be? 400. Okay, and then they did give us one in the middle four, right? And the middle four are these ones. So when they give you one of them, you can fill in the rest of them. So that's actually really nice. So you can see here, we could either figure out this cell, right? Because we know these have to add to 200, or we could figure out this cell because we know that these two cells have to add to 600. So well, let's figure this one. What's this going to be if it equals 200? So this will be 150. And what is this cell going to be? 550. Okay, and then finally, this one, there's two ways we can calculate it. You can go 550 plus what equals to 800. Let's just do it that way, right? Or we could go this way, right? What plus 150 equals 400? What did you guys get? 250. Okay, so that's really nice. Okay, so there wasn't enough room to continue, so we'll continue on the back. So before we answer the question, let's make sure we know what we're asking. If the events are independent, then that means that someone who participates in extracurricular activities is no more or less likely to know what he or she wants to do after high school than someone who doesn't participate. So, knowing whether someone participates in extracurricular activities gives me no additional information about whether they have post-high school plans. So, in other words, the probability of choosing someone who knows what they want to do after high school should be the same as the probability of choosing someone who knows what they want to do from among only people who participate in extracurricular activities. So, A, find the probability, right, that a person who knows what they want to do after high school. Okay, so we're going to have to go to our chart up above, and if we want to find that probability, let's see here. So the probability that someone knows does yours look like this? No? Okay. I modified it. So, and I shouldn't have modified it before I taught it. Okay, that's all good. So the probability that they knows, that is part A still, right? And so this is going to be, so we're going to look at our table, and the probability that someone knows what they want to do after high school, that's, there's no given, so we're looking at the total. So it's going to be 800, right, out of the 1,000. So I'll go here. So when we do that work, that's 0.80. So the next one, I believe it says, find the probability of a person who knows what they want to do after high school, given that the person is in extracurricular activities. Okay, so notice here, it's given that the person is in extracurricular activities. So when I look at my table, I'm going to go back up here. Okay, if it's given that they're in extracurricular activities, then we're only looking at this column. Okay, and we're looking at, let's see here, let me write this down. So we're looking for the probability that the person knows, given they're in extracurricular activities. So let's look up here. So the person knows, isn't that the 550 in that column that they know? And if we're only looking at that column, then that's going to be over the 600. Are we clear? So let's go down here. So this is going to be 550 divided by the 600, which is when you divide it on your calculator, you get 0.917. Now that becomes a calculator problem. So 91.7%. Okay, are they the same? So, right, if so, we have independent events. If not, we have dependent events. So does this one here equal this one? So the answer is no. So let's write no down here. So therefore, you can say they are dependent events. Or we could say that they are not independent. And a lot of times they say not independent, I've noticed in this curriculum. Based on your answer in 3B, that point 917, if you knew someone who had plans after high school, would that affect your guess for whether or not the person participated in an after-school activity? So based on your answer to 3B, so 3B is asking the probability that they know, right, given that they do extracurricular activities, right? So it says if you knew someone who had plans for they have plans for after high school, would that affect for your guess for whether or not the person participated in an after-school activity? So notice here, I think a good way to go here, right? The probability. I'm going to have to kind of cram this in here. So probability of extra, right, curricular activity, if we look up here. So extracurricular activity, that's going to be the 600 this time, right? Out of the 1,000. Which is equal to 0.60. Or 0.6 is fine, obviously. So there's a 60% chance. Okay, but then they say, well, what about if the probability, right, of extra, given that they know what they want to do after high school? Okay, so, okay, well, that's going to be, so for given that we know, that if I go up here, I'm sorry for going back and forth, we are just looking at this row, right? If it's given that we know. So if we're looking for that they are in extra curricular activity, it's still the 550, but this time it's out of the 800, right? So let's come down here, and that's going to be equal to the 550, but that's out of the 800 because we're only looking at the row. And when you stick that on your calculator, you get 0.688. So does that change how we might guess? Are they? It's still not they're still not the same, right? So not the same. So therefore, dependent events. Okay. Are you guys okay with that? Do the calculations determine if the events are independent? So basically saying do the calculations, right, that we have up above. So if we want to do the calculations here, so notice here, I'm sorry, I skipped this right here. It says, let's also explore using our current tool, the multiplication rule that we learned in a previous lesson. If the events are independent, then the probability of someone participating in extracurricular activity and knowing what he or she wants to do after high school should equal this, right? the probability of participating in extracurricular times the probability of knowing what you want to do post high school. So let's write out what the actual equation would be here. So the actual equation would be, let's see here, it would be the probability of doing extracurricular and knowing should be equal to, right, we're going to check to see if it is, the probability of doing extracurricular times the probability of knowing. Okay, well, we did find the probability of extracurricular right here. So I can do this here, and I can write the 0.60 times, and we did do the probability of knowing. Whoops, it's the wrong color, or the wrong tool. Here we are. Probability of knowing, we did that all the way up here. It's at 0.8, so I can take and bring this all the way down here. Okay, and then the probability of knowing, right, and extra and knowing, this is whole chart, right, so we're going to go back up to my chart. The probability of doing extra and knowing, that's going to be the 550 out of the 1,000. Is that clear? So let me go down here. So this is going to be the 550 divided by 1,000, which you guys would probably just write that as the decimal right away, which is 0.55. And we're checking to see if this is equal. And we're going to multiply these together now. 0.6 times 0.8, isn't that 0.48? Okay, so is this equal? So that's a false statement. They're not equal. So therefore, the events are not independent, right? See how they like to say not independent? So they are dependent. The next question, 6, do your answers to 3 and 5 agree? And the answer is going to be yes here, right? Because they were both show that they were independent, okay? Yes, so both methods lead to the same conclusion. Okay, how are we doing? Can I go to the next one? Okay. Can we apply this logic in reverse? Can you complete the table below in a way that would indicate that the two events uses a computer and is making a math class? Can you make the table so that they are independent? Well, we can. Okay, so let's come down here. It says, according to the information we already have, let's answer the following questions. So it says, what's the probability that a person uses a computer? So we should probably look at our table here really quick. This first row right here that I underlined is in a math class, and so this would be not in a math class. And then this column here, uses a computer at least 3 times a week, does not use a computer 3 times a week. Got it? So what's the probability that they use a computer 3 times a week? Well, isn't that going to be the 600 over 1,000? Probability is taking a math class. Well, what's that probability? Well, is taking a math class. Here's math class, right? So this is this row. This is the total. And we're going to put that over 1,000. So this is going to be 700 divided by 1,000, which is 0.7. I'll add an extra 0. Part C. I think this might be just a little different than what you have there. It says, therefore, if they are independent, then we know that the probability of uses a computer, we need to find probability uses a computer and taking a computer, right? What will that equal? Well, won't this be equal to the probability, right, of using a computer times the probability of taking math? Okay, and we found that using computer right here. So it's going to be the 0.60, and the probability of math is 0.70. And when we multiply those, you get 0.42. Now that's if they are independent, right? They're telling you it is independent, so then what would the number have to be? Which of the table, in our table here, up above, what cell does it correspond to? The probability, right, of using a computer and taking a math class. Which one? It is cell 1, right? So down below, we're going to start filling that in. So we're going to take that information. All right, cell 1 here. And let's take and put this into cell 1. So that's going to be 420. Okay, and so now we get to fill this in. So 400 so let's figure out our total columns first. That'll make it nice and easy, right? So 700 plus what gives me 1,000? Isn't it 300? And let's figure out this one here, right? 600 plus what equals 1,000? 400. Okay, so what do I add to 420 to get 600? And this is 180. And then here, right, 420 plus what gives me 700? 280. And then this is probably just the easiest. 180 plus what gives me 300? 120. Okay. So your notes look a little different because I think it's all on one page, if I recall. So I'm going to have to go back and forth here a little bit. It says here, we have tried to make the events in mathematics class and using a computer at least once a week for schoolwork independent. If they are independent, then knowing whether someone uses a computer should not give us any extra information about whether or not they are in a math class. So therefore, the probability, right, that you're in a math class should equal the probability that you're in a math class using a computer. Okay, so let's calculate that. So probability that you are in a math class. So if I come up here, there's no given, so we're going to use our total, right, the 700 out of 1,000. Which gives me the 0.70. Okay, and then we're going to do the probability that they're in a math class given that they use a computer. Well, okay, so if we're given that they use a computer, that's going to be this column here, and if they're in a math class, that's going to be the 420 out of the 600. When you divide those, you get 0.70. Do these values agree? Yeah. So therefore, it's independent. Which they had already told us that it's independent. We came up with our numbers based on them being independent, but they're just showing, this is another way of showing independence, and so they're showing that it also works. Notice also it says here, but we also, right, could choose to compare the proportion of students who use a computer regularly with those who use a computer regularly among those in a math class, or given that, right? So let's compare those as well. So the probability of using a computer, so if I look here, probability of using a computer, we're looking at totals. That's going to be the 600 out of the 1,000. Which is 0.60. And then B, right, you're going to find the probability that they use a computer given that they're in a math class. So, okay, fine, let's go back up here. If we're given that they're in a math class, then we're just looking at this row right here. So using a computer is 420 divided by the 700, 420 divided by the 700. So it's going to be 420 divided by 700, which is 0.60. Okay. Do those numbers agree? Yeah. So therefore we could say they're independent based on that. Hey, how are we doing? Should we do the Titanic example? It says here, in 1912, the Titanic was struck by an iceberg and sank. Tragically, there were not enough lifeboats to accommodate all the passengers. Based on what you know about the Titanic, do you think there was a relationship between the class someone was staying in and whether they died? If so, what do you think the relationship is? If not, why? So, like, when they say class, right, they're talking like first class, right? Second class, right? So the first class would be the nicest rooms, right? And then second class, not as nice. And then as you keep going down, it it's the cheaper, right? So do you think that there was a relationship between what class you were staying in, how expensive the room was? What do you guys think? At this point, you can't be wrong because we're not looking at data, right? Do you think it matters? Huh? Why? Are you starting to look at the data? Okay. You can look at the data, and so you're looking and so you're saying that first class, it looks like the data is showing that more first class people survived. Okay, so what's the implication then? Rich people survive, poor people, right? Drowned. So, but is that true, right? So let's look at the data that we have here. So I'm going to keep moving here. Number 12, it says, your friend tells you she heard that people who stayed in first class in the Titanic were much more likely to survive the sinking than people in other classes. In other words, she thinks that whether a person survived was dependent on class. What calculations can we do to determine whether a first class passenger was more likely to survive than others? Okay, well, there's a couple of things that we could do, right? Okay, one, we could compare the probability that they're in first class with the probability that they were in first class given that they survived. Okay, or two, we could compare the probability that they survived with the probability that they survived given they were in first class. Give you a second to copy that down. There's actually a third way, right? You could figure out the probability that they were in first class and survived and see if it's equal to the probability that they're in first class times the probability that they survived, right? And see if those are equal. Okay, can we move on? Okay, so the following table gives information about adult passengers that died and which survived. So use the information to calculate, to do the calculations described in 12. Okay. So so using, so we're going to do that. I'm just going to do one of those two calculations, right? I'll do both actually. So let me divide this space up here. Yeah. Let's do method 1 described above here and method 2 over here. So this says look first at the probability that they are in first class. Okay, and then we'll compare it with the probability that they were in first class given that they survived. So I'm literally taking the these two up here, right? I'm doing the first one here. Okay, and then for method 2, I'll do the second one. So looking at my chart, the probability of first class, if we look here, probability of being in first class, well, we don't have any given, so I'm just going to look at the total, right? So it'll be 319 out of the 1,207. So it'll be 319 divided by 1,207, which is approximately 0.264 when you divide that on a calculator. So for the next one, right, we're looking at the probability that they're in first class, but we're given that they survived. So if they're given that we're survived, we're only looking at this column here. And so the probability that they were in first class would be 197 over the 442, which when you put that on your calculator gives me 0.446. Do these match? The answer is no. So are they independent? So they are not independent. Method 2, if you remember correctly, we're going to look at the probability that they survived. And we're going to compare that with the probability that they survived given they were in first class. Now, you don't have to do both. The minute you discover they're not independent, you're done. But I just want to show you that you can do it both ways. So the probability that survived, that's the 442 out of the 1,207. And so you can see here, when you put that on the calculator, it's approximately 0.366. So now this time, right, we're given that they were in first class, so we're only going to be looking at this row right here. So you can see that's going to be 197 that were in first class, these ones, and then the total for that row, which is the 442, which when you put that on the calculator is about 0.618. Okay, so you can see here that these also are not the same, right? They do not match. So either way we go, right, you'll get that it's not independent. Okay, part B. What did you find? Is first class independent of survival rate? Or does knowing a person stayed in first class give us extra information? So, and we basically say that they are dependent events. So that's the first thing we find, right? So you could choose your method, right? So the probability of surviving is significantly higher than surviving. Than just surviving. The probability is higher that you survive given you're in first class, right, than just surviving. So let's keep moving. Part C says, suppose we know there were 319 in first class and 442 survivors, but didn't know how many of the people who were in first class and survived. if being in first class and surviving were independent events, how many of the first class survivors would we expect? How does this compare to the actual number? Okay, well, so remember here, I'm going to break this up here. So this is going to be if it were independent. Then the probability of it surviving, I'm going to abbreviate here, and being in first class would be equal to the probability of surviving times, right, the probability of being in first class. So the probability of surviving, right, would be the 442 out of the 1,207. And then we have to multiply that by the probability of being in first class. So first class is going to be the green row that we have here. That's going to be the 319 out of the 1,207. So this gives me, when you divide 442 by 1,207, you get 0.264. And when you divide 319 by 1,207, you get 0.366. And when you divide those, you're going to get 0.097. Are you guys okay with that? Now, that's not how many survivors that we have, right? Survivors given and that they were in first class. So in order to calculate that, right, I'm going to take that percent, the 0.097, and I multiply it by the total number of passengers, which is the 1,207. So that would give me, when you multiply those, 117. So if they were independent events, notice here, the number that's in this location would had to have been 117. But it was 197. That's 80 more passengers, right? So we can see that it's therefore a more significant, right? And more significant number of, there's a significant difference in the number of people that are in first class, right? That survived, right? If it was independent, it would have been 117, but we had that it was 197. Okay, D. If you were told that a randomly selected adult in the Titanic, I'm sorry, if you were told that a randomly selected adult died in the Titanic, would you predict they were in first class or not, and why? So if someone died, would you say they were in first class, or would you predict they were in somewhere else? Well, didn't we just show that there was a higher rate of first class people that survived? Right? So I would predict, right, that they are not first class. So here, the probability that they are in first class, given that they died, isn't that 122? Right, let's look up here. Right, if we know they died, so we're only looking here, and they were in first class. That's 122 out of the 765. And when you divide those, that's approximately 0.159 or 15.9%. So what about the other people? Well, we can find the probability of not first class. Given that they died. That's going to be 1 minus the probability of being in first class, given that they died. Well, we just found that, didn't we? The 0.159. So this would be 1 minus 0.159, which is 0.841, or an 84.1% chance that if you are not in first class, I'm sorry, if you knew someone died, there was an 84% chance that they were not in first class. Does that make sense? It's a little bit, you have to be careful of your wording. If you were told a randomly selected person was in first class, would you predict that he or she did or didn't die on the Titanic? At this point, I'd say did not die, right? So I can look here at the probability that they survived, right, given that they were in first class. Okay, so I can go up here, I can just look at the first class. Survived is 197 out of the 319. Which is approximately 0.618. So there was a 61.8% chance that if you were in first class that you would survive. Okay, are we okay with that? Ooh. Last thing is, it's important to note that dependence doesn't tell us anything about causes of such relationships, only that the two events have an association. So here it says, a random sample of U.S. adults was taken. People were asked their gender and whether they prefer coffee or tea when having a hot beverage. The results are summarized in the table below. If gender and hot beverage preference are independent, how many people should be female and prefer coffee? Right, so they're asking us to figure out, okay, well, they're saying if gender and hot beverage preference are independent. So that's going to be really important, and they want you to figure out what is the value then of this cell. Okay, and there's actually 3 methods that we could do, and then I put the summary up here because these are the 3 methods, right? You can find the probability. Let me break this up here into 3 sections nicely. So method 1, okay, using this one right here, right? Probability of A, right, is going to be equal to the probability of A given B. So in this case, right? I should probably write this is the probability of being female, right? Given that the probability of female and coffee. Well, we know, right, that the probability of being a female would be the 360 out of the 600. Bless you. Which is 0.60. So if I come over here, I can take the 0.60, and if they are independent, then this is given. I can't spell coffee. Oh my gosh. There we go. If we're given that they drink coffee, right, that's the 390, right? So I'll take that here, and I can multiply those, and that gives me 234. Method 2, you could find the probability of B, right, given, or it has to be equal to the probability of B given A. So in this case, then I would say it's the probability of coffee is the same as the probability of coffee given that we have a female. Well, the probability of coffee, that's going to be the 390 over the 600. Which is 0.65. So I would take that, the 0.65, and we're given that we have female. So out of all the females, that's the 360 that we have here. And we multiply those, you'll get 234 that way. Okay, and then the final method, we'll wrap up with this. You could do the probability of A times the probability of B. I'm just switching the sides, right? I'm doing this one, but I'm switching the sides. Is equal to the probability of A and B. I'm kind of running out of room. So this is going to be the probability of F times the probability of C is equal to the probability of A and C. So in this case, the probability of being a female would be the 360 over the 600. And the probability of coffee would be the 390 over the 600. So let's wrap this up. That gives me the 0.60 times the 0.65, and when you multiply those, you get 0.39. Okay? So there's no given here, right? So we're looking at the entire population, so it's going to be 0.39 times the entire population, which is the 600. And you'll get 234 that way. Okay, and that wraps up the lesson.